So, who think you get the final form? Who get the final form? Please raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. 8 people get the final form. So if we scale to the second highest, probably don't do much good, right? Arya, could you please check if the camera is on? Thank you. Okay. Homework. Have anyone finished the homework? Have you, Vega, did you take a look?
Yeah, the first problem.
You have done the first problem. How about Temitope? Finish the first one. Attempted. Okay. Who finished the first one? 1, 2, 3. 3 of you. Okay. Jiasheng, is it difficult, the first one? No? Okay, if you have stratified wavy, use 0.01 for something. And you have to use flow pattern program to do the calculation for the second one, right? Arya, yes?
The first question,
The first question. If it is not title Douglas, use whatever Shoham. If title Douglas doesn't work, use whatever in the book. Okay?
So, in the book, in the nodal class, you gave us the general form, the general map. So, using...
I asked you to do with the map or without the map? Okay.
To get the flow type.
Alright.
So, when you use the generalized map, you get to a region that's, when you put it in the flow pattern, it's not going to get the same.
So use the map. May get different results.
I get strata, what I got? I got stratified baby, but in the flow pattern, you get stratified.
So the map doesn't check transition K, does it?
Well, if we go based on the nodal class, we can go fast and get the answer that we used to, and you get the F value, you get but on your list of transition options, F is to check whether you are stable or not stable, and K is to check whether you are wavy or not wavy, right?
Yeah, after it's stable, then we have to check whether it's wavy or not wavy.
Yeah, stable, we may at least we can have stable. I made that stable. I used T, and T is supposed to be for transition.
So when you did not have any mistake, you get it the same?
Yes, wavy.
You got baby?
Yeah.
Okay,
You
Arya,
got baby?
we will check it later if
But in
for
flow pattern,
further
you get
question.
stratified.
Yeah, let us check it later. The question is designed for you to take about 6 hours to do it. Okay? It is not 1 hour, 2 hours, 3 hours or something. And in the exam, at least, okay, please make sure that you can do 1.1 by a calculator if it appears in the exam. Question, please.
Why do you get, okay, I attempted it and I got 2 different values of the EDL when I use liquid and when I use gas. And according to the theory, it's supposed to be the same thing.
Okay. Why is that?
Because we are reading off the chart, so maybe our HL is not very accurate.
It is usual that you get it different. And I can tell you, it is about the assumption that you do with the interface, tau I. Sometimes you use like Vg minus VL, sometimes you use just Vg square. So when I do it, it is not the same either. And I found that it is about the interface term. So in the exam, whatever you get, it is fine. Yes, Arya?
So about that, Professor, I used rho G minus rho L.
Okay.
The one you told us. Actually, the actual form. And at the end, so I got to something like for rho L, I mean for pressure drop for liquid, I got minus 40, and for the other one, I got, for example, 3. There was a huge difference. So I tried to figure out what's wrong, but I changed the H tail just a little bit. For example, it was 0.29, I changed it to 0.294. And now they're the same.
Oh, you didn't use 15-digit accuracy? That's probably what caused that.
How am I gonna get it from the map? I mean,
You don't need to
chart.
use
From the chart.
exactly, when you read the chart, you don't have 15-digit accuracy, right?
But
So that could cause those discrepancies
so
easily.
reading from the chart causing that much of error
Oh yes.
is useful. I don't want to say
So now you find out by yourself how reliable is the chart. When your peer engineer doing it and show you the result, you find that by yourself, right? How reliable that is. If you want it accurate, buy Auger, $1.6 million for 3 years license. 1.6. It is between 1.6 and 1.7 million dollars per license for 3 years.
But actually what I did was, at the end, I was supposed to have both of the values of pressure drop for liquid and gas the same. So I used gold sig to give me the right answer for...
Are they the same?
Yes, that is.
If you really want to have it very, very accurate, you solve it numerically, the dimensional form of the governing equation. Even so, it is not going to be like 100% correct, because you have already made some assumption on the shear stress, right, on the interface or something. Unless you don't make any assumption, it could be quite accurate, but it's not perfect. Whatever you do, okay, it's not perfect. Jia Cheng, how many hours do you spend on doing the homework? Could you please share it with your friend? Yes? 3? 3 hours. Yeah, okay. That's the first one, right? And the second one should be another 3 hours, maybe. I'm sorry, next to Vega, what's your name? I forget. Anders. How many hours for you?
I can take that. If it's, I only used to do that with maybe
1 hour for question 1.
no,
More than 1 hour. 2 hours for question 1. Okay. So I ask this because for those of you who have not tried or do anything yet, please be very encouraged to start very soon, because it takes time. Okay? And the homework costs, the homework weight more than the exam, right? Homework is about 10% or something. Yes?
I was just wondering, in problem 1, 2, are you supposed to use the liquid for what that you got in problem 1?
In 1.2,
What are you going to calculate?
assume that the flow pattern in 1.1 is dispersed bubble flow. Use the liquid HOA that you get from 1.1.
Okay.
So in 1.2, you assume that there are a couple ways of doing it, and I don't blame you for any approach. Let's say you use liquid HOA from 1.1, it's fine. If you assume lambda L instead to be used as HL, that's fine too.
Because they're pretty different.
They are pretty different, yes. So when you try, let's say you use HL for 1.2, it's fine. If you use lambda L for 1.2, it is also fine. So that if you copy from your friend, then I know. Okay, there are several approaches to do this. Okay. Who read the book. Of course you read the book. Who read the book about slug flow more? Did you read the book about slug flow? No, not much. Okay. Let me remind you about symbol variable definition. Subscript LS is for liquid slug. Okay. Subscript TB is for Taylor bubble. So VL TB is liquid velocity in Taylor bubble region or film velocity. VG TB is gas velocity in the gas pocket. Subscript LS is for slug body, right? So VLLS is the liquid velocity in slug. VGLS is gas velocity inside the liquid slug. This lecture,
What
we
do you
will
call LU?
LU slug unit length, LF film length, LS slug body length, LM mixing length, VTB interface velocity, which is highest. The purpose of this lecture, we will go through more in detail, okay, a little bit more in detail on how to do calculation of slug flow. So you see the tractor in your book, right? So this picture telling you that, okay, tractor move at the speed of Vs, slug velocity. But all those things in front of it move faster, okay, move at the speed of VTB. Because all this dirt accumulate, okay, and bounce each other. So this makes the speed of the stuff picking up by this tractor move faster than the tractor. So tractor pick up some soil, some dirt, right? But the speed of this thing in front of it move faster than the tractor itself. Okay, that's the idea that you have seen in the lab already. VTB greater than Vs. Okay, just that. All right, let's start with Douglas-Hubbard model. So mass flow rate, total mass flow rate at any cross-section area at any time is not constant. Okay, you can tell, right? Sometimes we have liquid, sometimes we have slug. Their model assumes that the total volumetric flow rate is constant throughout any cross-section of the pipe at any Z or any T. Volumetric flow rate stay the same. So this means there's no change in the density of gas phase. There's no like compression of the gas phase, expansion of the gas phase. Douglas-Hubbard model doesn't account for any of that. Douglas-Hubbard model assumes that there's no compression or shrink of gas phase or anything. Density of gas phase stay the same. That's Douglas-Hubbard. Is that going to be the same as the real case? Yes, for a short distance of pipe where pressure is more or less the same. Let's say we are at the pressure of 500 psi and within 100 feet the pressure drop from 500 to 495 psi. So that change of 5 psi will make the gas expand a little bit, will make the phase change a little bit, right? But it may be not much. Okay? So Douglas-Hubbard model, Vs is the same. Okay. Now, yes.
Doesn't that pressure function about
Can you speak to it?
Mass at any WL plus WG at any location, they are not the same. Let's say sometimes we have slug. So mass flow rate at that location is high, right? Sometimes we have mostly gas. So mass flow rate is like not much because almost half of this part, right? So if you look at the slug body, mass flow rate may be 2 kilogram per second. But if you look at this part, mass flow rate may be just 1 or 0.9. So at different location in the pipe, mass flow rate is not the same because density is not the same. Make sense?
Can you explain about the
Well,
electrical
you
circuit?
said you continue with them since last stuff.
Okay. Continuity equation. I have not shown you about the continuity equation for two-phase flow yet. Right? You have seen continuity equation in single-phase flow. Of course, divergent V equal to 0 for density doesn't change. That continuity equation, it is about if we have very small, infinitesimal small element incoming and outgoing mass in that very small control volume, they're the same. That's the continuity equation. Okay. Continuity equation also applies for every location in this part. But you have to do integration. So mass coming in and going out in that small unit volume conserved is not the same as mass going in and going out in this big volume conserved, right? I didn't say that it's not conserved, but I said mass flow rate is not the same. So this part and that part, W total is not the same. I think it's kind of somewhat counterintuitive. But if you look at the picture, this is because it is a two-phase flow. If it is single-phase flow, if you have liquid over here we also have liquid, right? And we calculate mass flow rate. In this part, let's say we have inclined pipe. Some part we even have a film flow backward, right? So in slug body, W will move forward, but in the film region, W will move kind of backward. So it's not quite the same, right? For double Hubbard work only for horizontal flow, just horizontal flow, no flow back or anything. So double Hubbard theta equal to 0, okay? Kind of volume in equal to volume out, but mass in is not quite the same as mass out at different location. It's not quite conserved or not conserved. They look at different location, okay? At different location, do we have the same mass flow rate? No, but at different location, we can have the same volume flow rate. Okay, so pipe doesn't expand or shrink. Clear? Not completely clear? Yes, totally.
Looking at that picture, which one is V and
VTB?
no V mixture?
Okay, we are going to talk about it, which one is which. Because this one is, use Taylor bubble as the frame of reference. Now we will analyze the pickup rate. Okay, we will analyze the pickup rate. We use Taylor bubble as the frame of reference. When we use Taylor bubble as the frame of reference, this means we move at the speed of Taylor bubble. So when we move at the speed of Taylor bubble, we will see the interface stationary, right? Stationary interface. Because we move at the same speed as the interface. But the material inside the interface moves backward, correct? Because the material inside moves slower than the interface. Make sense to you?
Professor,
Yes?
can you talk about volumetric flow rate that you say is the same everywhere? For gas?
So that is in stationary frame of reference, not moving frame of reference. This is moving frame of reference, so it's something else. For stationary frame of reference,
What do you mean by consistent in the other?
we put at that mark, right? Total volume that moves to this side is the same as when we put at this point and total volume move at that location. So at different Z, total volume per unit time or volumetric flow rate, they're the same. That is for, but mass is not the same. Is that clear? If not clear, please help me by read show handbook and come see me. All right. We move at the speed of telebubble. Okay. When we move at the speed of telebubble, we will see fluid particle inside the film move backward, right? Correct? We will see gas particle inside the gas pocket move backward too. Okay? So I put here relative velocity of liquid film is VLTB minus VTB. Okay? Negative value means this relative velocity is moving in the opposite direction with respect to VTB. I ask myself how quick that fluid particle in the film move backward. So if I move at the speed of telebubble, it will move backward at the speed of relative velocity, right? If I want to consider the sign, then I use the speed of fluid particle minus the speed of frame of reference. Okay? So if this one is positive, this means VLTB minus VTB is positive. This means VTB is higher than VLTB, or they move in the same direction, right? If it is negative, this means it move backward. Okay? Slug front is the frame of reference, this part. Okay? This is slug front. The liquid inside the slug move backward, right? But the liquid move to the slug front at the speed, at the velocity of, so what's this? Let me repeat again. Move this one. The liquid film move to the slug front. Okay, let's take a look at the liquid film. Liquid film is this part, right? This part is the liquid film. Liquid film move to the slug front at the speed of VTB minus VLTB when we don't consider sign. Okay, so if we just want to know the magnitude, we use higher value minus the smaller value, right? So the speed of liquid inside the film move backward is VTB minus VLTB. The speed of liquid inside the slug body move backward with respect to the moving frame of reference is VTB minus Vs. Okay, so when we talk about the relative velocity, it's just something minus VTB or VTB minus something. If we just want the magnitude, we use VTB minus something, and then it will be positive. But positive means move backward. Okay, so now we can do mass balance, right? Can we? Because everything is stationary. When everything is stationary, we can do mass balance by say that mass that go into this boundary is the same as mass that going out. Mass coming in equal to mass going out. Good. Mass coming in is with respect to moving observer, okay? For the moving observer, mass that coming in is the relative velocity multiplied by cross-section area. That will give you volumetric flow rate, right? Multiplied by density, that will give you mass per unit time. So the pickup rate is the relative velocity, which is VTB minus VLTB, multiplied by cross-section area, which is this small cross-section area, not the whole thing, okay? And that part, they say HLTB times AP, of course, right? H times AP is cross-section area that we have liquid phase. So velocity times area, that is volumetric flow rate, multiplied by density, that gives us mass flow rate. So mass flow rate that going into this boundary, okay, this red boundary, is that amount X. Make sense to you? More dear? No? What confused you? Relative velocity multiplied by cross-section area multiplied by density.
What is X?
X is the mass pickup rate. Mass per unit time that go into that red boundary. You see this red boundary? Mass per unit time that go to that red boundary, that pickup rate. Right? Because slack body pick up some mass and release some mass at the back.
Well, you also said
It's not
it's not equal.
Yes.
So now you said
Yes.
equal.
For X, right?
Your first said it's not equal.
It's not what is not equal is total W. Total W is not constant and at any cross section of pipe. That total W. Total W is not equal. X is right hand side, pickup rate. Right hand side is the pickup rate, right? The amount of pickup rate is, okay, when you think about the slug flow, it is slug body pick up some mass, right? How much mass that slug pick up? How do we know that? We have to move at the same speed of slug flow or at the same speed of the interface. When we move at the same speed of the interface, whatever pick up, that is the pickup rate. Okay. So initially we cannot do this kind of thing because we stay in the stationary frame of reference. In the stationary frame reference, we cannot do mass balance or anything because it changes space and time. Now we try to make it change just space, not time.
What about gas leak?
Oh, we are going to talk about that. Yes.
You have subscript E there. What does that mean anything?
That mean anything? That means something in your textbook because I copied this picture from your textbook. Subscript E, that is VLTBE. E is, I think, at the end or at the equilibrium film height. Forget about it for now. We will talk about it later. Yes.
So you're using the reference velocities multiplied by the hold up of the cylinder.
Area. H times A is cross-section area. That cross-section area, the red part.
Exactly. So I'm saying the cross-sectional area doesn't cover the whole pipe. Why are we using A of pipe?
A pipe is this much, right?
Yeah.
A pipe times HLTB will be just this much. And that much is that much when we look from the side.
Well, that's all.
Yeah, hold up is area occupied by liquid divided by area of pipe. That's hold up, right? So area occupied by liquid divided by area of the pipe multiplied by area of the pipe equal to area occupied by liquid phase.
It's not
Good? Not good yet?
No, you called it height.
Oh, okay. I apologize. Not high, hold up. Capital H. So we have a pickup rate. Of course, pickup rate, mass going into this part, in this red boundary, should be the same as this boundary, right? This dashed boundary. If not, this length will expand. Correct? So mass going into this red boundary should be the same as mass going into another red boundary, boundary 2. Make sense? So let's analyze what is the mass that going into this red boundary. So VLTBE is the speed at that point. Is the speed at that point. Okay. So mass that go into this boundary, let's call boundary 2 and boundary 1. Mass that go into boundary 2 will be, Akin, what do you think? Relative velocity, right? Multiplied by cross-section area, multiplied by density. Make sense to you? Okay. So relative velocity will be VTB minus VS. Cross-section area will be HLLS multiplied by AP. And then multiplied by density, which is rho L. which is this term, right? So when we take a look at mass at boundary 2, at boundary 2, mass flow rate that go to that boundary is relative velocity multiplied by cross-section area multiplied by density. This is mass that go into that boundary with respect to the moving observer. Okay, so this is what moving observer will see. Moving observer will see that mass that go into boundary 2 is that amount. Siri, what do you think? Make sense to you? Okay. Siri, which page number that has this equation? Or we never have this equation? Which page number in shorthand book? Let me change that. You find the page number? Page number is not difficult question.